Hi guys, I'm Michael, and today I'm going to talk about immutable collections. First, I want to give you some background about myself for people who don't know me. I'm a PhD candidate at CWI, which is the Dutch National Research Center for Computer Science and Mathematics in the Netherlands. And they're mostly doing research about efficiency of immutable collections, but also in how to speed up programming language runtimes, and also how to speed them up with data structures, and vice versa. So let's go, today's topic is collections. So what are collections? Collections are actually a group of objects. And how those objects are arranged, can be categorized by various categories, what kind of data type it is a list, a set, a map data type, how it is stored in insertion order, is it unordered, etc., etc. So the whole domain of collections is quite huge and has a lot of variability inside. So in today's talk, I'm not going to cover all kind of different collections that you might have seen already, but I'm focusing on a specific subset. And that subset is mostly concerned with how to efficiently get immutable unordered collections, unordered hash sets or hash maps on the JVM. Well, now that you know what collections are and what kind of collections I'm talking about, why would you want them immutable? And there are plenty of reasons why you would, for example, care about immutability. But just a few to mention is that once, from a virtual machines perspective, for example, or once you have immutable data, that unlocks a whole range of new optimizations, because you have stronger guarantees about your heap graph and what changes and what doesn't change. But more importantly, from a user's perspective, it gives you a simpler mental programming model, because you're just coding with values, and the values you have, they don't change. So there is no kind of you're leaking a reference to some other part of your program, and that probably corrupts your state of your collection. And last but not least, it's also in terms of concurrency, it's very robust, because your immutable collections, they're thread safe per se. So you can easily share them amongst different threads without having to fear that your state gets corrupted. Well, I would like to quote Joshua Bloch on his book Effective Java. And here's an item there where he says that actually classes should be immutable unless there is a very good reason to make them mutable. And I would like to make that more precise and say the same is true for collections. So you actually want immutable collections. The quote also continues and says, well, immutable collections provide many advantages, and the only disadvantage is the potential for performance problems under certain circumstances. Let me paraphrase that. I would say that immutable collections are challenging to optimize, but they constitute a more sensible default. So that's my opinion on the topic, and I would like to exactly focus on these 2 points in how to get them efficient and show you some things you can do with them that you can't easily do, for example, with mutable or array-based collections. So to do so, I'm going to break my talk down in 4 parts. First of all, I would like to introduce you to the core principles of what does it take to have efficient immutable collections, and some of the, for example, more well-known encodings therefore. Second, to talk about how to get the memory footprint down of such data structures. And then I'd like to continue in talking about, okay, once you have that, how can you get those data structures even more efficient and more expressive? And last but not least, I'd like to talk about, okay, what does it take to probably make them even faster in future on the JVM or in general? So let's start with the core principles. Well, immutable data structures. If you code with immutable data structures, that doesn't mean that you're stuck with your data and you can't manipulate it. In fact, you can, but you're deriving a new instance, a new copy, for example, that has values added or removed from them. And the important thing is how you implement that behavior under the hood. So what you don't want to do actually is that you first have to copy your whole data structure, Okay, probably like allocating like more space for a new element you insert. Then actually mutating the clone you created and then saying, oh yeah, from now on it's like immutable again. So here you would like have to copy the whole data structure. Well, what does make like or constitute of the core principles for efficient immutable data structures? So the first one is actually, instead of having like a large chunk of data, you try to split it up like in smaller chunks. And those smaller chunks are usually actually aligned in a sort of tree structure. Once you have such a tree structure, it's very, you can devise an update to the data structure as a sort of like delta, where you just encode the parts that changed. So in that case, you would just have to like clone a fraction of the tree and link back to everything that didn't change. So imagine like your previous data structure was really huge, had a few thousand millions elements. You can like implement that very cheaply. In fact, such data structures, they already exist on the JVM, and they're implemented like in plenty of languages there. So JVM languages like Clojure, Rascal, or Scala, all of them like have one thing in common, so that they have like strong immutable collection libraries, or yeah, collection data structures that are implemented exactly upon that paradigms. And they're usually implemented as hash array mapped tries, or let's say successors to that data structure. So what is a hash array mapped trie? Hash array mapped trie is exactly such a tree data structure. And one of the interesting things about it is that each node is just simply purely an array. So you implement nodes as an array, and you encode the prefix of the hash codes in the tree structure itself. Well, in this case particular, we will like encode like 5 bits each per level. And in order to make it more illustrative and how that works, I would like to continue throughout the presentation with a simple example, like a set of integers. And if I would encode that set of integers in the encoding I showed you before, I would end up like with that tree. It's like nested arrays, like where you have like segments of a fixed size. These segments here, for example, like 32 bits long. And those segments actually like mix data and like references to further subtrees. So I told you I'm going to talk about efficient immutable data structures. And for me, that doesn't look efficient, does it? It's like there is a lot of like empty slots that you're wasting there. Well, therefore, hash array tries, for example, use bitmaps in order to signal which of the array slots is actually in use and which isn't. So by doing that, we can compress, let's say, the conceptually 32 wide long arrays to just like arrays that are as tight as we need them to represent the data. On the left, you see like a Java like a code skeleton that tells you exactly that with like a 32-bit integer bitmap and like an array that can grow to that size. What can you expect, like performance-wise, from such a tree data structure? Well, first of all, they constitute like shallow and wide search trees, so that the trees that have a branching factor of up to like 32, and with 32-bit hash codes, that means like we get trees that are only like up to 7 levels deep. And by having like that shape of the trees, we have actually like performance characteristics for lookup, insertion, and deletion that are like in a very small log number. And the Scala community, for example, coined a phrase that they're saying like it's effectively constant, because it's like really, you have to traverse under like maximum amount of like a path of up to like 7 nodes to get there. One strong point of these trees compared to array data structures, for example, are that you can implement structural operations on top of them. So you can merge structurally 2 trees, for example, in implementing a union operation instead of like having to iterate over one and performing an insert for all the others. So that was a quick review of what hash array map tries are, and as said, those are already like present in a few languages out there. And the question is like, how can you make them like memory efficient? Because we are having 3 data structures, and those 3 data structures actually like have, by nature, a lot of like indirections. You have like nodes that point to nodes. And for the example to illustrate in how to make the memory efficient, I would like to make that code snippet even simpler and remove the bitmap, because essentially what we are having here is just like a compressed array list that like gets up to 32 elements wide. Well, we have a nested array here, or like a field which is of type array. And as you might know, on the JVM, like arrays are objects too. So they live on the heap. They cause you like a memory indirection, probably like cache misses. You have to allocate like extra headers like for the objects. You have a length field there. You might have like padding or alignment issues. So that gets back like to Brian's talk in like you want just like to optimize like a simple property of your program, but yeah, so there's a lot to do behind the scenes. So conceptually what we want in order like to have that efficient is not to have the memory indirections. And in that example, we might to think about like compile time specialization, where we just say, okay, hey, let's enumerate all the possibilities that we have. And in this case, we can just get up to 32 different like node configurations, and just emit like specialized layouts that contain the number of fields like inlined in the class just as much as we need them. Okay, that sounds great from the perspective of like footprints. So we get probably like better cache behavior, we get small memory footprints. But there are also like 2 properties that we get that we actually do not want to have. And that's like, well, we're getting megamorphic calls and also like a lot of code bloat. And why is that? Because we not only have to specialize the memory layouts, we also have to specialize the operations on the memory layout. So we are effectively like substituting a dynamic like structure for a set of like static structures. And that entails like a lot of like performance overhead on the runtime as well. Well, in the optimal case, we would like to have that picture, like where we are always happy. And that's like, we have small footprints, as I showed you before, but we get like the benefits of a dynamic structure of like having monomorphic call sites instead of like having to dispatch on the type and being JIT friendly, like not having to generate like all the specialized code just for purely accessing my specialized data layout. And that's possible to achieve as well. And the answer lies simply in decoupling like the data layout from the operations that operate on the data. Well, and in terms of our code snippet, so we just substitute like the specialization with something that looks like much more dynamic again. So in this case, we could, for example, as one of many possibilities, create an array view out of like subsequent fields of the same types that are like in an object array. Did anybody here see that, like such sort of like attempt already on the JVM? Well, essentially that's also like what Paul Sanders presented like last year here at the JVM Language Summit when he talked about the var handle API that's upcoming in JDK 9. And not only that you have like the opportunity to get handles like to variables or like fields, you also like have the opportunity to get array handles for different kinds of arrays. But one part is missing like from that proposal. That's exactly like having an array view on subsequent like fields of the same types. So Paul Sanders referred to that as some of the exotic features of the upcoming var handle API. And to my opinion, as far as I know, it's not going to ship like in the subsequent release. Well, once you would have such an abstraction, you can really like code with a specialized data structure as you would code with an array. So you have like array copy operations like on your client source side. And yeah, and you can implement and code it as you would like with a regular dynamic data structure. So that concludes the part of how to get rid of memory indirections in your tree nodes, for example. So to have specialized memory layouts, but not having the overhead or our extensive overhead for the JIT compiler or the runtime. At the same time, compared to the state what shipped in Scala or in Clojure, hash tries in the recent years also became more expressive and more efficient. And there I would like to go back to the example that I showed you before. So just the simple node layout and how the tree looks by side. Oh, by the way, I forgot to mention, if you have any questions throughout the talk, feel free to raise those questions. Otherwise, I take questions also at the end. So if you look at the data structure, you see color-coded, well, we're interleaving data, payload that we want to store actually, and the administrative overhead, so further references to subtrees. And that actually can get more performant as well. So just by manipulating the data layout, we can get speedups in iteration, for example, over established data structures up to 6x, six times so fast, and improve equality also by another magnitude. And that at the same time, while also reducing the memory footprint. Well, sounds too good, right? How is that possible? Well, first of all, if you have the interleaving between data values and subnodes, your data structure actually has to check at runtime what type it is. So you have to do an instance off check or some kind of dynamic check to decide, am I now having here a data value that I have to return to the user? Or do I have to go deeper and recurse while looking for values? And what we did is also we changed the compression function to not only get rid of the empty slots, but also to permute the elements along the way. And what that gives you is an encoding where you have on the right-hand side, you have then all the subnode references grouped together, while you have all the payload there as well. And in terms of iteration, for example, well, iteration becomes much more simpler. You just need to know the bounds, how many nodes, how many data values I have per node, and then how many subnodes I have. So you can yield all the data values in one go, and then just once recurse in the subtree, instead of going back and forth all the time. And yeah, so essentially all kind of tree traversals or tree processing operations profit from that sort of reordering. How did we do that? Well, essentially on the data layout side, we added yet another bitmap. So instead of just having one bitmap that tells you which slot is in use, we now have two 32-bit bitmaps that tell you as well what type it is. So we make it explicit. Are you having a subnode on that position, or is it the data value? Well, how can I save memory in just permuting, for example, some elements and adding yet another bitmap? And there's a lot of detail to that, but it becomes more obvious once if you look at a map encoding, for example. So maps would use two slots for the key and values, and because previously we just had one bit to say if a slot is used or unused, also subnode references occupied two slots. So you had a mixture of key value pairs and then empty slots and subnode references. Once you do the permutation, you can actually get rid of all these empty slots as well. So you save memory, but you also get better cache locality, and you can exploit that layout in the code. And keep in mind as well is separating or regrouping the elements that you have all the similar typed elements together. It's one of the key ingredients for later on exploiting different memory layouts. And that's also what I want to talk about now is how these data structures got more expressive as well. Well, just imagine you have a program that processes numeric data sets. And you want to store and process that with collection data structures, let's say? Well, if all your data fits in the 32-bit range, yeah, like you have like specialized like data structures for that. You can use like specialized primitive collections. So like the Java ecosystem offers you a wide range of libraries that specially optimize for that. And you get the benefits of like having the data stored unboxed and all the access passes to the data also like don't need boxing. Well, let's assume on the other side, you have a data that's more complex or like bigger numbers that don't fit into the 32-bit region. So you might have to represent them as a big integer object or something like that. Well, there we are already like covered at least like with immutable collections, because you can say you can just use generic collections as they are in the JDK. So they can be parameterized by type and, well, here you go. But what about if you now have like your data contains maybe a lot of numbers that fit into the 32-bit range, and some of them that are bigger? Well, can you express that with a primitive collection? Well, obviously not, because that's really like specialized in just storing integers or longs or whatever kind of you specialize for. So you're not able to express that with a primitive collection. Well, what's the other ways? Can you express that with a generic collection? And of course you can, but you're blowing up your memory footprint, because suddenly all your primitives get boxed. So what hash-array tries, or like successors to that encoding, allow you is also like to generally like store heterogeneous collections or heterogeneous data efficiently. So you can store efficiently unboxed integers or any kind of like value types in the future probably, along to references, and you're not consuming much more memory. So with such an encoding, it's actually possible to reach the memory footprint of specialized primitive collections while still having the ability to store references along. How does that work? Well, in the background, like you here see like a simple set as before. We have on the right like the subnode references. On the left, you suddenly have data mixed. So you have like here numbers and also like references to big integers. Once we exploit the similar tricks that we did before, in like once again permuting the elements, that now all the primitive data is grouped together and all the reference data is grouped together on the right, you can once again like exploit the differences in differently like specializing memory layouts. How does it work like with the permutations? Well, in principle speaking, what I showed you before is we had two different bitmaps that made it explicit what kind of data type it is. And you can see it also like as we have the state of like what type of node is distributed over two different bitmaps. Well, once you change that encoding and go back to a state where you have like one single bitmap, but like longer like bit sequences that tell you which state it is, you can also like dispatch on like multiple states there. And so that boils it down to how much heterogeneity you would like to support. So for example, with the same amount of bits as before, we can support like two different types. But you can also like grow that and say like, hey, I want to support many more types. So that's like a trade-off, and definitely entails also like trade-off decisions there. But that's how it works conceptually. I would like to say that actually that kind of encoding that I presented you is orthogonal to like different approaches. So one of them is like to union types in Scala that approaches like that sort of like heterogeneity like on the type level that you can express it at least. But it's also like orthogonal to primitive generics that are like coming up in Valhalla. Because what the encoding gives you is like a separation and the regrouping of the values. So like that all of them are grouped together. And then you can like make it explicit, for example, with generic types in and specialize it later on. So that concludes how they get more, like how hash-array tries got more expressive and performant recently. But what about the overall performance and performance challenges with the data structures? Well, as said, here we're working with arrays, with trees. Those trees are like very shallow, but still they're trees. And what we would like to have is like that for any kind of operation, like that we have trees that are as fast as arrays. And one way to tackle that, or like at least to reduce further like the penalty that you have for the tree data structures, is improving the locality of like our between different nodes. So the specialization approach I showed you before is concerned with locality within a node. But if we have a tree data structure, there's also like all the locality concerns between the nodes. If you have a simple or a single tree, you can imagine something like laying it out like flat in memory and then just having like forward jumps, like log n forward jumps to find your data. And that's something like the Java memory management subsystem or the garbage collector, for example, could take care of in like being more aware of like what data you're dealing with. But the story is not that simple because, as I told you before, like once we modify those data structures, we actually get all these deltas. And deltas are actually linking back to the original state. So instead of having a single tree, what we actually get is a forest of trees. And then it doesn't become that obvious like how to represent that efficiently or locality-wise in memory. So that's like, I would say, a very open-ended question like in engineering and also like in research in how to, for example, allocate those deltas or in generally how to deal with those forests, let's say, on a like virtual machine level. But I would say personally that it's definitely possible like to still reduce further the performance gap between like trees and arrays. And there are many, many aspects where trees already like shine and outperform like mutable collections and also like array-based implementations. But there's still like a performance gap for some of the operations. So to sum up, I was first presenting, let's say, the state-of-the-art of hash array tries as they are like implemented in several languages that already exist on the JVM. Then I was talking about how to get those tree nodes more efficient by specializing them and what kind of like dynamic exercise it would need in order like to treat specializations still as a dynamic data structure. Furthermore, I was telling you how hash array tries got more efficient, and that was mainly achieved by permuting how the elements are stored in the tree nodes itself. Then I was focusing on how they got more expressive, and more expressive in the sense of that you can also efficiently store heterogeneous data there. So for example, like unboxed primitives or value types along to references. And in the end, I was sketching like some of the still remaining performance like parts or like issues that we need to address in order like to make them yet faster. Well, as a takeaway, I would say that Java already caught up in the last years, for example, with Java 8 and the Stream API in providing functional abstractions in Java. But what's still missing, or what we still have, is like we apply that functional abstractions on mutable data. So we are missing effective and efficient immutable collections on the JVM or in the JDK. So some of the more details about what I was talking today, you can find, for example, on that GitHub repository. And there are also like links to scientific papers and also like implementations where you can dive into or like which you can use. And with that, I would like to close and thank you for your attention. So I'm happy to take questions.